Picture this. You need to process a massive dataset containing 10 million lines. Loading everything into a list could eat up gigabytes of RAM. Your program might even crash before it starts. But never fear, using a generator will chew through this task with ease. That's because generators use something called lazy evaluation, which means they compute and deliver one item at a time, only when you ask for it. Think of it like taking one piece of pizza out of the box each time you're hungry, rather than taking the whole thing out in one go. This means no waste and less overhead. In this video, we'll cover how generators work, how to create them using functions or expressions, as well as their performance characteristics and real-world use cases. Okay, with that out of the way, let's jump in. Before diving in, let's go through a quick refresher on iterators and iterables, because these are key to understanding generators. If this is your first time hearing about these, I've linked a more detailed video and article covering iterators and iterables below. In Python, an iterable is anything you can loop over, like a list, tuple, set, string, or even a file. If it works with a for loop, it's an iterable. But when Python starts looping, it doesn't just pluck values out of thin air. It calls the built-in iter function on the iterable, which returns an iterator, a special object that knows how to give you the next item in the sequence. So you can then call next on that iterator until it's done. Let me show you how that works with a quick example. Here my list is a list, which is actually an iterable. Then when we pass my list to iter, we get back an iterator that keeps track of where we are in the list. Each call to next gives us the next value. But when we run out of items, it raises a stop iteration exception. Now normally you don't see any of this under the hood. Python handles it all for you inside a for loop. That's why the loop ends gracefully, because Python is catching that stop iteration for you. So the for loop that we've got here is actually secretly doing something like this under the hood. Now writing your own custom iterators used to mean building a class and defining the iter and next methods manually. But generators make that a lot easier. Now that you understand what an iterator is, let me introduce you to a friendlier, more Pythonic way of building them. Generators. Here we've got a function which allows us to count down from a certain number until it reaches 0. The main thing to notice is the yield statement, which is what makes this a generator function. Remember how an iterator is an object with a next method that returns values one at a time? Well, a generator does the same thing, but you don't have to write a class or deal with any boilerplate. Instead, you write a function and use the yield keyword. Calling countdown doesn't actually run the function. Instead, it returns a generator object, which is a type of iterator. You can use next on it, just like we did before. So just like a custom iterator, the generator keeps track of its internal state. Each time you call next, Python jumps back into the function right where it left off, resumes from the last yield, and runs until the next one. And yes, when it runs out of values, it raises a stop iteration too, just like any proper iterator should. So here's the tie-in. Every generator is an iterator. It's just a much more elegant way to build one. In fact, any function with a yield inside it is automatically a generator function. No special decorators or convoluted boilerplate required. Let's talk about one of the most important differences between a regular function and a generator function, and it all comes down to return versus yield. A return statement ends the function and hands back a value. Once you return, the function's done. It's gone. But a yield? That's a little different. Yield pauses the function mid-execution, hands back a value for now, and says, "Hold my spot. I'm not done yet." It's like putting a bookmark in a novel instead of tossing it in the fireplace. Take a look at these two functions. If we call the regular function, we get a single value back, 42, and that's it. But when we call the generator function, we don't get 1, 2, and 3 immediately. Instead, we get a generator object. Then each time we call next on that object, the function runs up to the next yield, spits out a value, and pauses itself, waiting for the next time we want it to continue. Here we've created the generator object and called next on it a few times. Each next resumes the generator from where it left off, almost like hitting play after pausing a video. And just like before, when it runs out of yields, Python raises a stop iteration so we know it's done. Generator expressions give you a quick way to define generators inline instead of using a function. They look just like list comprehensions, only with parentheses. The standard list comprehension that we've got here allocates all 5 squares up front. This means if we print out the squares list, the whole list will be populated straight away. The generator version, on the other hand, computes each square only when you loop through it or call next for each item. This makes generators lazy, which is perfect for when you're working with large or infinite data. Generator expressions are great for one-pass transformations without polluting your namespace by creating a separate function. By now, you've seen how we can consume generators using next quite a few times. And yes, next is how generators actually deliver their values one at a time. But in the real world, you're almost never going to manually call next over and over again, like we're doing here. Instead, you'll let a for loop do the heavy lifting. What's happening here is deceptively simple, but really elegant. Behind the scenes, that for loop is automatically calling next on the generator until it hits a stop iteration. No need to manage state, no need to catch exceptions, just loop until it's done. And this is where generators truly shine. They give you all the benefits of lazy evaluation, generating items on demand, but with the clean syntax of a for loop. It's also worth noting that you can loop over a generator only once. After it's exhausted, it's done. No rewinds. If you want to start again, you'll need to create a new generator. When people talk about generators, one of the first benefits they love to bring up is efficiency, especially when it comes to memory. And they're not wrong. Generators can be much more memory-friendly than lists, especially when you're dealing with a lot of data. Let's break this down with an example. Here, we're creating a list comprehension and a generator expression, both with 1,000,000 numbers. But take a look at their memory footprints. The list comprehension holds all 1,000,000 items in memory at once and uses about 8 megabytes of memory. The generator expression? It only keeps a tiny internal structure, just enough to know how to get the next value when asked. This results in the generator using less than 200 bytes of memory. Okay, so that's memory. But what about speed? Here's where things get a little nuanced. You might think generators would be faster too, but that's not always the case. In fact, building a list all at once can sometimes beat a generator if you're going to process all the items anyway. In this test, we're summing 50 million numbers. First, we time how long the list comprehension takes, and then we time the generator version. When we run the code, sometimes the generator is faster, sometimes the list comprehension pulls ahead. This is due to how lists handle data storage and access. Lists materialize all their elements in memory upon creation, allowing for direct access via indexing with big O of one-time complexity. This means retrieving any element from a list takes constant time, regardless of the list's size. Generator expressions, on the other hand, generate values on the fly and don't store them in memory. While this approach is memory efficient, it introduces extra overhead, which takes time. So what's the takeaway? Generators are great when you don't need all the values at once, or when you're working with very large data and memory becomes a concern. But if you're going to consume everything in one go and memory isn't a problem, a regular list might be just fine, and is actually faster in many cases. If this helped you out, give it a like, subscribe for more Python tips, and check the links below for the full blog post, which covers generators in more detail.